Thank you for joining us today for our talk on instantly bringing Unity games to players on the web. We have some new web features you can try today, as well as some really exciting things to share that are coming in the near future. I'm Ben Craven, a senior technical product manager at Unity, looking after web platform. This is Anthony Bowker, a senior engineering manager on, you guessed it, web platform. So first, I want to talk a little bit about where Unity has been and where we're going from here with the web. As some of you may know, Unity has quite a bit of history with web runtimes. In 2013, the Unity web player debuted as a plugin for web browsers. This solution was short-lived, as it was deprecated 2 years later in 2015. Then, we adopted WebGL to run games directly in the browser with asm.js. Unity was there at the beginning of the WebAssembly design process, and we've been evolving alongside WASM ever since. This brings near-native performance of the Unity engine to the web. In 2018 TechStream 2, WASM became the default and replaced asm.js. Now, you haven't heard from us in a while, but we do believe we're at a tipping point for Unity content on the web. So why are we doing this? What makes the web powerful? It's incredibly powerful for two reasons. Offering content in this way offers end users that feeling of instant access as they're taken into an experience with just a click of a link or a scan of a QR code. And there's no need to install something onto their device. In addition, when you bring your content into the secure environment of browsers, you have a direct connection between you and your users. There's no app store to get in the way. I thought that was a pretty good point, too. So web doesn't have an installation step like other platforms, which brings the promise of low friction and instant engagement. However, this means users need to download the runtime and starter assets on first load. So for us, for you, our creators, and all of our end users, load time is everything. There's a ton of work being done to reduce load times, and you'll hear more about that in a few minutes from Anthony. So the depth and breadth of Unity Engine gives you the power to handle more complex simulation and interactive elements compared to other web technologies. That said, with users downloading the runtime and starter assets up front, smaller is almost always better in the context of web, at least for now. Given those trade-offs, there are certainly some types of game content that work better on the web than others. Here's a couple of examples. First, there are casual and hyper-casual games with their bite-sized play sessions and easy-to-grasp mechanics. These are perfect for the web. The other example here capitalizes on the low-friction nature of the web by taking a small part of a larger game, say your tutorial level, and make its own web build separate from the rest of the game, and making it available for all users. This allows for a frictionless first-time user experience without installing anything on their device. Then, you can convert the user to the full native app after they've engaged with the mechanics or wherever else your game lives. These are just two examples, and we're looking forward to seeing all the other creative methods creators will think of to harness the potential of interactive content on the web. It was awesome to see that NASA used Unity to build this, the Artemis Real-Time Orbit website, or ARROW. NASA does love their acronyms. An interactive real-time tracker for the Artemis 1 mission launched last November. For those that aren't aware, Artemis is the son of Apollo and will be the series of missions that marks NASA's return to the moon. Using this web app, space fans around the globe could view where the Orion capsule was in its orbit, as well as see its eventual splash site down in the Pacific Ocean. NASA is planning to build on this tool for all future Artemis missions and expand it to track not only the Orion capsule, but all other mission components. So you can use Unity to bring rich, interactive, real-time 3D experiences to the web for your next lunar mission or whatever other marketing activities you have. Now, you may have noticed that I've been talking about devices and showing pictures of phones. It's really odd since Unity has never supported web builds on these devices. But if you saw our keynote, you saw that we have heard your feedback. And there was a lot of it. These are all actually real customer statements made in a single month. So thank you all for being vocal about this. But we've heard it, and I'm proud to reiterate that Unity 6 supports mobile browsers. Thank you. So what does this mean? It means you can run your Unity games anywhere the web exists, including in iOS or Android browsers themselves, embedded in a web view in another native app, or use our progressive web app template to make your game behave more like a native app with its own shortcut. We're confident developers targeting web on mobile will have success with high-end mobile devices released in the last 2 to 3 years, but this will vary quite a bit based on the content. By the time we ship Unity 6, we'll have clearer guidance around the min-spec for web on mobile. Here, you can see our recent 2D sample project, Happy Harvest, running on Safari on an iPhone 15 Pro. Some might be asking, well, why roll out support now? What took us so long? Well, a few things have changed in recent years. First, Safari started supporting WebGL 2, so Unity Web works on iOS as well as Android. We've seen continuous advancement in both mobile network speed and reliability, as well as the ever-marching progress of improved CPU and GPU power. Finally, modern audiences have an appetite and appreciation for instant experiences with very low friction. We've all experienced this to some degree with the proliferation of short-form video content. For these reasons, we believe users are primed for short-form gaming content. Speaking of which, as you may have heard in our keynote, we're partnering with Meta to build support for their instant games platforms. Now, what are instant games? Well, it's where users can find and play games instantly on Facebook and inside Messenger conversations. With an audience of gamers in the hundreds of millions, this is a fantastic new platform opportunity for Unity developers to extend their content's reach to an entirely new cohort. There are a number of things the Unity Web team is working on to facilitate this partnership, including a dedicated build target so you can test, build, optimize, and publish your games in a streamlined flow tailored for the instant game use case. There will be a C# SDK to interface with instant game APIs, and a multitude of net new optimizations to ensure users can get into games in seconds. We're also partnering with game studios to prove out and validate this new tooling as launch partners. Now, one of those studios is CodeSync, who have a few games on Meta's platforms, including this one, Ready, Set, Cook. The team at Unity applied some early optimizations to this game, and the results were super promising. With just a 25% drop in load time, there was a 50% growth in active sessions, and a jump from 35 to 58% click-to-play rate. This means that with just the beginning of our optimization work, Ready, Set, Cook went from most players never seeing gameplay to the majority getting into a game with their friends. This is the result of just the tip of our optimization iceberg, but you can see how relatively small reductions in load time can make a huge difference in engagement. But enough numbers, let's see this in action. So here you can see comparison between the original build provided by CodeSync and the optimized version with our latest instant game ready tools applied. Now pay attention, because in the instant game world, things happen very fast. So imagine you're inside an application, you receive a challenge from a friend, and you say, accept, I will play this. And it's the first time you've ever seen this game. So I'm waiting. Oh, I see something. Oh, and it loads. And you're in. 5.5 seconds. The original build, we're still waiting. We're still waiting. Ah, there we go. So we went from 12 seconds time to interactivity to just over 5.5. Thank you. So this particular test was run on a Pixel 5, throttled to 48 megabits per second. So there's no, high bandwidth trickery going on here. Let's take a look at some more numbers across different speeds. I need to click that. So here you can see what the load times were before optimization and where we're currently using Ready, Set, Cook as a testbed title. First, throttle to 48 megabits per second, as we all just saw on the previous slide. This is the global median mobile network speed as reported by Ookla. It's not even 5G. At the global median broadband speed, 86 megabits per second, we're even faster. And finally, on a median 5G connection here in Amsterdam, we're a bit faster, but you can see we hit diminishing returns as the speed stops being the primary limiting factor. Andrew Moe is the product lead for Facebook Gaming, and although he couldn't be here in person today, he wanted to offer this statement. We share his and Meta's belief that there's a ton of potential in making games instantly accessible, especially when paired with the social graph. Unity and Meta are both eager to see more Unity creators have success on these platforms. So now you might be asking, how the hell are we doing this? Well, to talk about that, I will pass it off to Anthony.
Thank you, Ben. So sadly, we didn't find a load fast button hidden in the drawer that we could just use. We've had to really look at all aspects of the web application to see how we can improve that download and initialization within the web browser. So let's take a quick look at the anatomy of a web game. First of all, it consists of that WebAssembly. That's the binary executable that contains the Unity game engine and all of your game logic. There's a large resource file that goes along with that, .data. This includes global metadata and asset resources for that first scene. You may also have asset bundles and addressables if you've used those to divide up the assets in your game. And then there's a WebGL template, the HTML page, and some JavaScript files to get it all going. So to begin with, there's some best practices that you should follow to create a good release build. Firstly, make sure you select the release build options and optimize for size. That allows our C compiler and linker to do the best job for you. Next, make sure you use compression. Brotli compression is the best, and we can have a setting where we can pre-compress for you as part of our build step. When you do that, you need to make sure that your web server is configured properly. And then we looked at adding HTTP preload tags to the WebGL template as well. This makes sure that any asset bundles or addressables that are used first are preloaded right at the beginning when the page is loaded. And we'll be making sure that these are the defaults in that upcoming instant game build target that Ben mentioned. Next, you should think a little bit about what the user's doing while they're waiting for your game to load. Consider replacing just a simple progress bar with something useful, maybe a splash screen or a video informing them how to use the game. But we need to continue to go further with this. So let's focus a little bit more on that WASM file, that WebAssembly file. This is already fairly well optimized. First, we do what we call managed stripping. You've seen this in the build settings, where unused .NET classes are removed. Then the IL to CPP compiler generates C++ code, which we pass to our C compiler. There, the linker does a sort of whole program optimization where it looks for various dead code elimination and other optimization passes that it can do. but still we have a fairly big WebAssembly file. And this is because Unity is a very rich general-purpose game engine. There are things in there, functional components, that are there just in case they're needed by your game. We have APIs where you can load resources from any URL on the internet. And so we've identified some of these subcomponents that at build time, you can identify that you don't need them and strip these further from the code as well. On the right-hand side, we can see a list of some of the subcomponents we're currently working with. And those that are crossed out are those that we could remove from that Ready, Set, Cook game. Once we've removed them, we then do a further optimization pass, which gives the linker another chance to do more inlining and perhaps dead code elimination for those pieces that are removed. And in this example with Ready, Set, Cook, we removed 1.5 megabytes from that uncompressed WASM file. And we're really only just beginning in putting together these subcomponents. These will be available again in that instant game build target, and there'll be a mechanism for you to select them manually and tools to identify which can be safely removed. So this helps get the build down even smaller still. Another benefit with this is that as well as downloading a smaller payload, there's less work for the browser to do when instantiating a smaller WebAssembly file. And this is great on mobile. Let's take a look now at the assets that we have. That's the other main piece of the puzzle. And so again, depending on your game, the assets may be bigger or smaller than the corresponding WebAssembly. And so here there are a bunch more best practices that you need to employ. Since that time at the beginning is super critical, consider using the Unity addressable system to break up the assets and only load those which are needed for the first scene. Then, other assets will get loaded on demand as they're needed as you progress through the game. If there's lots of audio in your game, consider reducing the quality of that, use compressed audio, and so forth. Likewise, we have suggested settings for graphics. ETC Crunch gives the smallest texture sizes and saves again on that download time. If you're using ASTC compressed textures, look carefully at the block sizes used in different textures and try increasing them. It still looks really good. Likewise, there are settings for shader stripping and graphical quality that you should look at. We'll be producing some better documentation next year, outlining how to best use these settings to the greatest effect. Putting all of these things together is what you need to get the fast start time that we need on the web. So that WebAssembly technology that we talked about, this is really foundational for how we can run Unity games on the web. And as Ben says, gives us that near-native performance. This technology isn't standing still. And on the web, we're really grateful for the whole work that the web community does to advance and support these technologies. Web gaming just isn't possible without the investments and supports from other browser vendors, and we particularly appreciate the collaboration we have with the Chrome team at Google. Together, we've worked on strengthening gaming use cases for WebAssembly and graphics performance for complex gaming workloads. So first, we have the mscripton toolchain. This is what takes that C code that comes out of IL to CPP and builds it into the WebAssembly for the web. With each new LTS release of Unity, we've brought the new mscripton toolchain to you, and each one of those reduces the time taken for developer builds. So if you've done web builds before on a fairly old version of Unity, try the latest one. You'll find that the development builds are now much, much faster. Likewise, we're enabling much more optimization settings from that LLVM compiler and linker. Those release builds now take longer, but they give you much more optimized builds. There's a 4 GB memory feature coming. Currently, in WebAssembly, your games are limited to 2 gigabytes of memory that Unity can use, which is fine for most games. But for more complex real-time 3D experiences, particularly when using desktop browsers, often you want more memory to loading richer, bigger scenes more dynamically. And so in Unity 6, you can now turn on 4 gigabyte memory support. And the work we've done here paves the way for future 64-bit memory support for even bigger memory limits. There's a couple of more WebAssembly features coming too. If you look at your code, you often use exceptions to catch error cases. When you have that turned on with web builds, with WebAssembly, there's been some overhead to having that. Turning on native exceptions in WASM allows you to still have that exception support, but with very little overhead. So again, we're shrinking down those build sizes for you. And finally on here, we've now enabled WASM SIMD. This is a newer feature that's come to WebAssembly, and it accelerates any mathematical calculations you're doing on the CPU, and replaces those single instructions with vectorized instructions. It works on both desktop and mobile devices as it maps those WASM instructions to the appropriate SIMD, SSE, or ARM Neon. A good example of where this makes an impact is in character skinning. With web builds, you do this with CPU at the moment. And when we've turned on the SIMD support for the character skinning, we can see improvements that range from 7 to 20%, depending on the browser and device that you're using. So if your game title has a lot of mathematics in it, or a lot of complex manipulation in your code, turning this on could have a noticeable impact just for clicking a button with Unity 6. These features are, however, only available on some of the newer browsers, so they are build options that are coming. So depending on whether your user base moves forward to newer browsers and newer devices or not, you can choose them optionally. But it's not just WebAssembly that's moving forward. It's a fantastic time for graphics on the web with WebGPU. And WebGPU is really a significant milestone for graphics on the web. And it really paves the way for the next set of unprecedented leaps in graphics rendering performance. WebGPU is designed with modern GPUs in mind and brings those capabilities to the web. In the browsers themselves, WebGPU is built on top of DirectX 12 or Vulkan or Metal, depending on your device and machine that you use. Similar to other modern graphics APIs, it provides that potential for more optimization opportunities, both on the CPU, due to the more modern nature of the API, and the GPU, because of improved throughput. And for the first time, it brings compute shaders to the web. And if you've been listening to many other talks that happen here at Unite, compute shaders is one of the technologies that's going to underpin graphics features going forward. So we're really excited that this is coming to the web, and we'll continue to bring web games along with those new features. Thinking of that skinning example we just saw that was done on the CPU, we can accelerate that further with a compute shader with GPU skinning and have that massive parallel capability on the GPU. Another example is Unity's VFX graph, which uses compute shaders to manipulate that geometry, again, all on the GPU. Let's take a look at some demos. First one of these is something that you may have seen a long time ago. This is Boat Attack, which is one of our sample projects we have. Here it is running on this Mac M1, entirely on WebGPU. The frame rate is here cranked up to what, 120 frames per second?
When it's not hooked up through this, yes.
Yes, when it's not hooked up to our video
Capped
system.
to 60, unfortunately, but
But it works really, really well. The next one of these is Viking Village. Again, this is a sample that's been available on our asset store for a long time. Here it is on Unity's graphics backend, running on web GPU. And when it gets going, it is better than 2 frames per second. So I'm not sure it's quite correctly measuring it there. We've been focused on building our graphics backend to get web GPU up to parity with WebGL. But let's see what else we can do with it. We talked about that character skinning. Here we're using GPU skinning to mesh this robot onto the skeleton underneath. If this was done on the CPU, it would be running at about 7 frames per second. So we can now really see what the GPU lets us do with things like this. You can move it around too. And finally, we have VFX Graph. Here we're doing a particle simulation. In this simulation, we have just over 500,000 particles being animated. And they're all being moved through compute shaders on the GPU. So let's see. Where do we go from here? Web GPU is available today on Google Chrome and Microsoft Edge on both Mac OS and Windows. And our graphics team at Unity has been working really hard on Web GPU. And with their development, we've been working really closely with the Chrome team again at Google to stress test those web GPU implementations with really large scenes and complex shaders that we use in games. And it's really beginning to produce some fantastic results. Our web GPU backend is still in development, and we don't yet recommend using it for production use cases. However, early access is available today. If you go to the Web Platform Forum, you can find a pinned post which will tell you how you can try these demos and how you can try it for yourself in the latest Unity 2023.3 alpha. We can't wait to see what you're going to make with this on the web. Host it somewhere, give a link to your friend, and get them straight into this level of graphics fidelity. Now I'll pass it back to Ben.
Thank you, Anthony. Live demos are awesome, always. And it's always wonderful to see beautiful scenes running in a browser environment, easily accessible. Now, we have one more thing to announce today. The platform of WebGL is now known as simply Unity Web. Why are we changing this? Well, we want to separate WebGL, the technology, and Unity's web platform. We also want to prepare for a future with more than one rendering standard, as Anthony just gave a glimpse into the future with WebGPU. You'll be able to create a build using WebGL, one with WebGPU, or a single build with both. So to recap, web is incredibly powerful because of its potential for frictionless engagement and a direct connection with your users. Because users download the WASM and starter assets up front, reducing load time is critical for web projects to realize that frictionless potential. And because of those trade-offs, their typically smaller pieces of content are best suited for the web, at least for now. We're investing a lot here, and we're so excited for you all to use the new optimization tools tailor-made for web projects. As far as what's coming soon, mobile web support starts in Unity 6. Coming late next year, build and deploy your instant games to Facebook and Messenger to access a whole new audience. And if you're the tinkering type, go read our forum post about WebGPU, which is coming to early access, well, right now on that alpha. And that's it for our presentation, but we would be happy to answer your questions if you have them. We'll head over here. Thank you.
Thank you.